Okay, good afternoon, everybody. We'll go ahead and get started. So yesterday I got some more test stuff posted on Brightspace. I don't know if anybody noticed it. I put up a sheet about test information, kind of all the good to know stuff. I did book the undergraduate physics lab to write our test in. That's room C2038. We call it the big lab. If you did physics 1020 or 1050 here, that's where you would have done your labs. So your,
Right there?
yeah, big room right in there. Your lab is in room 2039, 2038 is next door, so the big lab next door. So we're gonna write in there, it's a room set to accommodate 90 people, so we should be pretty comfortable in there. There's 61 of us, we'll be nice and spread out. I got most of the answers posted to the practice stuff, so that's up there. I'll post the cover sheet of your test soon and the equation sheet soon. Just wanna make sure I'm not gonna change anything first. And the cutoff for the test was the end of last lecture, so everything we do from now out will go on the second test. Okay, I think that's everything I wanted to mention about the test. Any questions? No? Okay, good. One more reminder, you gotta have a calculator. I'm not gonna have spares, so you need to bring one. So yesterday, we talked about electric field lines, some of the symmetries, and then we answered a whole bunch of questions about what's in the box. That's what this pre-class is about. And we finished up with two thoughts, and that was asking, when we talked about what's in the box, did the box have to be real? And did it actually have to be a box? So we're gonna come back to those questions today, and that's where we're gonna start. So, first of all, does the box have to be real? No, of course not. It's completely imaginary. We don't have to haul out a cardboard box every time we want to talk about electric field. Okay, so the box doesn't have to be real. And the box also doesn't have to be a box. It just has to be a surface. It can be a sphere, a cylinder, a box. Those are the three most common. So for a definition, a closed surface, so this thing is not straight, it's gonna make me crazy. Oh, and then. Okay, now that's what I get for touching it. Okay, so a closed surface through which an electric field passes is called a Gaussian surface. All right, so when we talked about the box, that box was called a Gaussian surface. It's completely imaginary, it's completely mathematical, so it's not a real physical surface. And when we choose Gaussian surfaces, and I would say that this may be the bit that people find the hardest about this section, is knowing how to pick the right Gaussian surface. The way you pick it is that your Gaussian surface should look like your charge. If you have a point charge, your Gaussian surface is a sphere. If you have a line of charge, your Gaussian surface is a cylinder. If you have a plane of charge, your Gaussian surface is a little box. So it should have the same symmetry, because that makes dealing with the integrals possible, or easy, one or the other. So when we talked about these things yesterday, the relationship between these arrows and the surface is very important. It gives us information. If the arrows point out, the charge is positive. If the arrows point in, the charge is negative. If we have more arrows, we have a bigger charge. So those arrows in relationship to the surface is a very important thing. So we're going to define the quantity that talks about those arrows with regards to the surface. And that quantity is called electric flux. So what is flux? Maybe that's a word people are familiar with, maybe not. From the dictionary, flux is the rate of transfer of fluid particles or energy across a surface, so something through something. You would get a flux of water out your garden hose. It is not related to the flux capacitor from Back to the Future at all, or the flux from the recent Doctor Who, so not those. Electric flux, this part is important, let's underline this bit, is a scalar quantity. Remember, scalar means it's not a vector. And it represents the number of electric field lines penetrating a surface. It has a symbol of a capital phi. Your book puts on a subscript of E for electric flux. We'll come around to magnetic flux later, and that'll have a subscript of N. Just be careful, phi here, we also used already for phase constant, so be careful with your symbols, you don't get them mixed up as you go. This electric flux, it depends on how strong your electric field is, so the magnitude of the field. It depends on the size of the surface, and it depends on the tilt of the surface relative to the electric field. The units of electric flux are newtons per coulomb times meters squared. So let's talk about how flux depends on these things. So what I did was I drew a bunch of arrows. That's supposed to represent electric field lines. We know flux represents the number of lines that penetrate through a surface. So let's say my cell phone is going to be my surface. It's a rectangle. If I look at it now, I've got all this number of lines penetrating through the surface. If my lines were denser, if I had more of them, then more lines would cut through. Obvious. Okay. So that's how the density of the field lines or the strength of the field lines matter. For the size of the area, so right now I've got a big area, I've got lots of lines. If I flip it, I've got a smaller area, I've got fewer lines. So the size of the area matters. And then the angle also matters. If I hold my phone this way, all of the lines cut through. If I hold it this way, none of the lines cut through. And if I hold it this way, some of the lines cut through. So the angle of that tilt matters. So I'm going to trace that. So there's the angle of my surface. This line has two components. It's got a component that's perpendicular to the field. So that's the perpendicular part. And it's got a component that's parallel to the field, parallel. I'm being a little bit lazy. I'm just showing the symbols for perpendicular and parallel rather than writing out the words. What we might notice here is that lines cut through this perpendicular surface. They do not cut through the parallel surface at all. So through this surface is no lines. Through this surface is all the lines. And the number of lines through the whole surface that we set up, the number of lines through this surface, is the same as the number of lines through the perpendicular surface. So the lines cut through the perpendicular bit, but not the parallel bit. So these two, same number of lines. So this shows us that the strength of the field matters, the size of the area matters, and the relative angle between the area, the surface, and the electric field vector matters. So let's get our math definition by thinking about how those things matter. So rather than draw it myself, I nabbed pictures from your textbook because your book is better than me. Up here we have the 3D pictures. So here's your upright surface, which is perpendicular to the field. Here's a slanted surface. So partly perpendicular and partly parallel. And down here we have our side views. So we know, we just established that the number of field lines, or the electric flux, it depends on the electric field, and it depends on the amount of area that's perpendicular to the electric field. As a shorthand, I'll call that A perpendicular. So let's start with our upright surface, the one that's perpendicular to the field. Let's say that our surface has a length that we'll call L, and a width that we'll call W. That's not showing up very well, is that? There, that's a little better. So that's on our 3D picture. On our 2D picture, up to down, that's our width. The area of our surface is equal to L times W, and all of the lines cut through this surface. And we take this surface and we tilt it. So instead of being upright, we slant it. That's what it looks like here, and it's slanted over here. Let's write down what we just established on our previous slide. If we've tilted our surface, then the lines through the total area A is equal to the number of lines through the perpendicular surface and that's a little bit of shorthand again. That's the part of the surface that's perpendicular to the electric field lines through the perpendicular surface, which we call A perpendicular. Okay, so we're building on that idea that we just established. So now the question is, how do we write down what is A perpendicular and what does that give us for our electric flux? So our dimensions don't change. We've simply tilted it. We've got the same length. This is our width here. And the width of the perpendicular bit, we could label W perpendicular. Okay. Now we'll come down to our side view or our edge view. There's our width. Our perpendicular width is the part that's perpendicular. And we've labeled the angle here theta. So our area perpendicular equals our length times our width perpendicular. You notice our width perpendicular, this makes a right angle triangle. W is the hypotenuse, W perpendicular is the adjacent. So W perpendicular is W times cosine theta, because it's the adjacent of a right angle triangle. So that's L times W times cosine theta. L times W, that's our area. So A perpendicular is equal to A times cosine theta. People who are real good at geometry, that may have popped for you right away, but this is how we get to that step. So now, let's make our conclusion about flux. Our electric flux is the electric field times A perpendicular, because it's the number of field lines through the surface. The number through the surface is the number through the perpendicular surface. That's equal to E times A times cosine theta. People doing or did Math 2050 maybe recognize this? That's a scalar product. Okay? So our electric flux then is the scalar product between electric field and area. Okay, questions? So it's a scalar product between the electric field vector and the area. Let's do a very super quick review of scalar product. So, scalar product is what you get. It's a way of multiplying two vectors to get a scalar for an answer. So just a number for your answer. It can be positive, it can be negative, it can be zero, but it is a scalar. It does not have direction. There are two ways to calculate a scalar product. So A dot B, you can find it by multiplying the magnitude of A times the magnitude of B times the cosine of the angle between them. This angle theta can get a little bit tricky. The important part to remember, how to figure this part out, is you draw A and B. So draw vectors A and vector B. You have to draw them tail to tail. Right? So there's vector A, there's vector B, their two tails are touching. Then your angle theta is between them. And is less than 180 degrees. Okay, so our theta is this angle in here. Some people argue that you can take this outside angle, but that's not how you find scalar product. Okay, so it's always the inside angle, so the one that's less than 180. So when you're finding these, lots of times you're going to have a problem. You're going to be given an angle, it may or may not be the same angle that's in this equation. You have to think about that really critically so that you find the correct angle. So you could be given lots of different angles. You've got to make sure you find the right one. The other way to calculate a scalar product is you multiply the x components, multiply the y's, multiply the z's, and you add them up. Both methods give you the same answer. They both give you the scalar product. But sometimes you're going to know the magnitudes and angle, you use this value. Sometimes you're going to know the components, you use this method. So it depends on what you know, which one you use. The most important thing to remember is that because it's a scalar, the answer is a scalar. I know that seems kind of laughable. That means when you write down your answer, there's no I, there's no J, there's no K, there's no direction, there's no up or down, left or right. Lots and lots of times on a test, people have to calculate things like flux, and they give their answer with a direction. And even if you get everything right, if you put a direction on it, you're not getting full points, because you have to recognize that it's a scalar. You would have come across scalar product, or I expect you've seen it in Physics 1050 when you talked about work and power. So those were scalar products. Work is force dot distance, power is force dot velocity. So that's where they would have came from. If you're a little bit rusty on it, if you go to the review section of Brightspace, there's a review on it, how you use it, a bunch of examples, and I think I've got some videos posted as well. Okay, so there's stuff there if you're a little bit rusty on scalar product. That said, we'll take our time going through some of the examples. So this is for if you're really rusty or brand new to it. If you're only a little rusty, what we do in class may be enough. Okay, are we still good? Okay. So next, let's come back to flux as the scalar product between electric field and area. So I would guess that everybody's okay with the idea that electric field is a vector. We related it to force. We know force is a director. It has a direction, and the direction matters. But maybe the idea that area is a vector is a new concept to some people. When you talked about area in your math class in grade 8 or whenever it is you learn area, I sincerely doubt you ever put a direction with it. But area is a vector, and it has a well-defined direction. So if we ask area is a vector, we shall say yes. And our area vector, this is the way your book goes through it. Your area vector is parallel to what we call the normal vector. So normal, in physics class, you're used to hearing normal with the normal force, and the normal force is always perpendicular to a surface. So our N here with the hat on it, that's the normal unit vector. It's a unit vector that's perpendicular to a surface and points out of a surface, just like the normal vector does. So N is our normal unit vector. It is perpendicular to the surface. And it is out of the surface. So then our area vector will also be out of a surface. So area is out of surface, is perpendicular to the surface. And it has units of meters squared typically. Once in a while, you'll probably use centimeters squared or millimeters, but typically meters. Yeah.
So those two lines in between A and X, that means they're parallel?
Parallel, yeah. A is parallel to normal unit vector. Yeah.
I'm sorry if it sounds silly, but what does it mean by out of surface?
Oh, that's such a good question. So for out of surface, why don't we do an example of how to draw the normal vectors and the unit vectors. So here's my water bottle. That's a closed surface. We could think of this as a Gaussian surface. I could draw arrows two ways. I could draw it this way. That would be into the surface. I could draw it that way. That would be out of the surface. So that's what out of surface means. And we'll do it on the box and the cylinder. Let's start here though, because then here we'll get into the nitty gritty of your question. Here's a flat surface, like a sheet of paper. If I hold up a sheet of paper, how do you know which way is out?
Good question.
You don't, right? You can't possibly know because out is both ways. This is out and this is out. If this were a test type question and you had to find the flux, I would do it in one of two ways. I would either define the area vector for you. I would tell you if I meant up or down, or I would ask you for the magnitude of the flux. That would take care of it either way. So very insightful question. So let's draw some of our vectors. So for our flat surface here, I'm just going to go with up for my normal unit vector, which means my area is also up. So right here, the area vector would point up. It would have a magnitude of length times width because it's a rectangle. When we get to a cylinder, things are a little funny here. If we look at the top, the normal unit vector points up. So at the top, the area vector points up. If we looked at the bottom, however, the normal unit vector would point down because it has to be outward from the surface. So the area on the bottom points down. And if you looked at the side of the surface, the normal vector would be radially outwards from the side. So typically when we do flux problems, you're going to be drawing surfaces. You'll always draw these normal vectors and these area vectors just to make sure you have it in the right direction. So for a cylinder, you can't just say up, down, left, or right. It depends on what part of the cylinder you're talking about.
Is there like a specific ratio for the normal force to the area, or is it just the normal force is always going to be smaller? Just depends on the example.
Oh, okay, so then that kind of goes back to a definition of a unit vector. So I hat is the unit vector that points in the x direction. It has a magnitude of 1 and no units and points to the right. Our normal vector has a magnitude of 1, no units, points out of the surface. Area will have the same direction, but it will have its own value. So for example, it's pi r squared here, length times width here. This n always has a value of 1. Yeah. So to answer your question, no. Yeah.
Are we ever gonna have to define like the IJK pieces of the normal unit vector? Like,
Yeah, we'll use IJK in there as well.
So I'm sure we'll get to an example with that.
We will. Okay, and then let's do a couple on our box. So for our box, the unit vector on top is out, this side is out, front is out, down is out. Okay, so whichever side of the box you're looking at points straight out, and your area vectors will all be length times width in those same directions. Okay, so we're all comfortable with area as a vector? So now, we'll kind of talk about what I wrote in brackets here. Electric flux as the scalar product of E dot A, and I tend to write this in brackets underneath where I write down that equation. I said this form applies to constant electric fields in areas that are not weird, okay? Which is a funny way to say it, but I can't think of a better way to say it, so I'm going to stick with it till somebody gives me a better idea. So I've got that repeated on the next slide. Let's go to that one. So typically, we're mostly going to use this form. But not always. Okay, so when we have constant electric fields, no variation, you know, it's 1,000,000 newtons per coulomb in a given direction, and our areas are something that we can deal with. There's squares and rectangles and spheres and cylinders. That's when we can use E dot A. However, what if our area is not perpendicular to the field? What if the electric field is not uniform? And what if instead of a sphere, we have some sort of weird shaped blob? How would we find the electric flux in that case? Because flux still exists. It's the number of field lines that penetrate that surface, so it's still a thing. So, let's go back. What if? So what we'll do, if we have this sort of odd surface, is we'll take our surface and we'll break it into small pieces. And we'll say we break it into many small pieces. Every single small part will have a little bit of area, its own area. Since it's a small piece of many, many parts, we say that that area is dA. So we would have one here, one here, one here, 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 and so on until we cover the entire surface with all those small bits of area. Those dAs are vectors, so let's say it points this way. So straight out of the surface, whichever way it points. Then what we do is we calculate the little bit of flux through that little area. So we find the small flux. Since it's a little bit of flux, it's d phi through each small bit of area. And we would find that little bit of flux, d phi, equals the area dotted with dA, which often you'd end up writing E times dA times cos theta. So we break it into little bits of a surface. Each one has area dA. We would find a little bit of flux through each surface. And then our net flux is the sum. When we have a sum of many small parts, that becomes an integral. So electric flux then would be the sum of all of our little bits of flux, d phi, the integral of d phi, which would be the integral of E dot dA. This is the general form for electric flux. We are going to be using this form and doing some integrals, but we won't do any integrals that you haven't seen in Math 1001. So, you know, power law integrals, stuff like that. So it shouldn't be anything you haven't seen before. And I think there's no point in asking what people are doing in Math 1001 because every math section kind of does their own thing in their own order. I don't think they're getting on the same page at all. But anyway, yeah, we'll have the standard that I expect everybody can do power law. That should be okay. So let's do some examples. For our first example, we're going to find the electric flux through the surface we show in the picture. The picture shows a lot of information. So my area is a little square. It's got dimensions of 10 centimeters by 10 centimeters. Right off the bat, we know it's going to be easy to find the area length times width. In this picture, I've got the normal unit vector defined. It points up, so that gives me an idea of the direction of the area vector. And the picture shows the direction of the electric field vector, which is 30 degrees relative to the surface. So we're going to put all these things together and we're going to calculate the electric flux. So I'm going to give you a minute to try that on your own. So there's our equation. And as you try it, I'll just write out the definition of scalar product again. most people are done with the calculators, so I think most people have mostly gone through it. So let's write down our equation for flux. Electric flux is E dot A. When you're calculating the scalar product, you've got two choices. You can go magnitude and direction, or you can go components. Magnitude and direction is the way to go for this one because we know the magnitude of E. You can calculate pretty fast the magnitude of A, and we have a direction. So let's go with the first method. E times A times cosine theta. Let's get our ingredients written down, what we know to plug in. E is easy, that's just given. E is equal to 320 newtons per coulomb. Area is pretty easy. 10 centimeters, 0.10 meters, times 10 centimeters, 0.01 meters, equals 0.0100 meters squared. Theta, maybe it's easy, maybe it's not. It's probably very tempting to put in theta equals 30 degrees, but we have to think about it. So let's go back to what we said about scalar product and how we find theta. You have to draw your two vectors. So we have to draw E and A, and we have to draw them tails together. So my E vector is already drawn for me. I'll highlight it there. There's my E vector. My area vector is parallel to my normal vector. So I'm going to draw my area right on top of my normal vector. There's my area vector. And my angle theta is between the two vectors. There it is on my 3D drawing. I'm just going to copy that again down here. So my electric field vector is up at an angle like this. My area vector is straight up like this. Here's the angle theta that I put in my equation, and the angle I know is this one, 30 degrees. When you copy it out like this, what the angle you're supposed to put in should really pop out at you. The angle we want is this one. That's a right angle, so theta is 90 minus 30 or 60 degrees. So we'll put in our numbers. 320 newtons per coulomb times 0.0100 meters squared times cosine 60 degrees. And we get for our answer 1.60 newtons per coulomb times meters squared. If you put in theta was 30 degrees and you got a different answer, I guarantee you're not the only person who did.
On a test, do you want us to show how we got the angle theta, or just it would be sufficient to write theta equals 60?
You need to at least put it in this diagram. Yeah, you gotta show where that's from. Otherwise, I'd probably just accuse you of making up angles out of thin air.
Okay.
All right, so let's go to another example. So for our next example, we've got a 2 centimeter by 3 centimeter rectangle lying in the XY plane. Okay, so I've got my XYZ coordinate system here. And this mostly is going to be all three-dimensional stuff, X, Y, and Z, I, J, and K. So let's call 2 centimeters my L value. So this will be the length. And I'll call this one the length. Let's call 3 centimeters my width, and I'll make this dimension my width. What is the magnitude? Well, notice here I said magnitude of the electric flux through the rectangle if these are my electric fields. So we'll do part A and leave part B for homework. Because I'm asking for the magnitude, it doesn't matter which way you take your area vector. If you take it up, you'll get one answer for the flux. If you take it down, you'll get the same magnitude, but you'll get an opposite sign. We're asking for the magnitude here, so regardless of what you get for your answer, you're going to take the positive and represent that as your answer. Okay, so we want to find the electric flux. Let's write down our equation for electric flux. Electric flux is the scalar product between electric field and electric and area. So it means we have two ways to calculate it, EA times cosine theta, or the component method, EXAX plus EYAY plus EZAZ. Two equivalent ways. This time we seem to know a lot more about components. So let's use our second method here. If you wanted to, if you preferred to find the angle between the electric field and the area, using your geometry skills, you're certainly welcome to do that. You'll get the same answer. But let's try it with the component method. So we know we're going to need all of the components. Let's go ahead and list the components of electric field. Then we'll figure out the components of A. Then we'll use our equation and find our flux. So for part A, the x component of my electric field is the part before the I hat. So EX equals 100 newtons per coulomb. EY is the part before the J hat. There is no J hat, so the part before the J hat is 0. So no Y component. EZ is the part before the K hat, so that's minus 200. There's my components of electric field. Now I need to deal with area. So let's draw our normal and let's draw our area vector. I'm going to put my normal vector straight up. My area vector is parallel to that. So if I want to figure out my area vector, I know that it has a magnitude and direction. The magnitude of my area vector is length times width, because it's a rectangle, so 0.02 meters times 0.03 meters, give me 6 times 10 to the minus 4 meters squared. So that's the magnitude. The direction, we figured out when we drew it. It points straight up. Straight up is the y direction, so the direction is j hat. So we'll write area as our vector. So it's the magnitude with its direction, j hat. So now we see area as our vector. We should be able to write down the components of the area vector. It only has a y component, so the x component is 0, the z component is 0, and our y component is the whole thing. So now let's come back to use our equation. Our electric flux is EX, that's 100 newtons per coulomb, times AX, that was 0, plus EY, that's 0, times AY, 6 times 10 to the minus 4, plus EZ, that's minus 200, times AZ, that's 0. So our electric flux to this surface is 0. And that kind of makes sense when we look at it. Our electric field has an x and z component. If you were to draw it, it would sort of look this way. It would be cutting through that plane, so edge onto the plane. The plane, the surface of the plane is parallel to the field, so there's no flux through it. Okay, so for part B, we'll leave that one for homework. This time it's not going to be 0, but you should still be able to follow through the same method and get to your answer there. I will post the answer, of course, so you can check it. So let's start another one that's going to roll into kind of a nice meaty homework problem for you that hopefully is going to help you really solidify this. This one's similar to what we just did, but not exactly the same. So we have an electric field, it has X and Z components, it's in the vicinity of a cube, so this entire cube is our Gaussian surface. It has a linear dimension that we call A, so every side has a length A. So this is A, this is A, and this is A, because it's a cube. The part we'll do here in class is determine the electric flux through the front face of the cube, which I shaded in yellow, so the amount of flux through there. We'll start by writing down our equation for electric flux. We've got components here, so we'll use the component method. So if we want to do this, we should figure out all of our components. Components of electric field are pretty straightforward because they're given. My x component of electric field is 2 times 10 to the 4. There's no j hat, so my y component is 0. And my z component is 2 times 10 to the 4. So my components of electric field, pretty straightforward because they're all given. Area vector, we'll do similar to what we did in the last problem. So we'll draw that normal unit vector. That sticks straight out of the surface. Here's the normal unit vector. And our area vector is parallel to that. Here's our area vector. So we should write down our area as a vector. And last time we really took our time writing it down. Maybe we can just shorten it up a little bit this time. So our area vector will have a magnitude. The magnitude is the area of the face, so A times A, or A squared. With a direction, the direction is straight out of the face. That's in the Z direction, which we call K hat. So 0.01 meters squared K hat is our area vector. All right, now that we've identified our area vector, we can write down the components of our area vector. Ax equals 0, Ay equals 0, Az equals 0.01 meters squared. So we've identified the x and y components of both of our vectors. We can come back to our flux equation, put in our components, and figure out the net flux. So for our first one, Ax is 0, so that first term is going to go down to 0. Ay is 0, that second term is going to go to 0, and we're left with Ez times Az. So we're just multiplying the parallel terms. So our net electric flux is 0 plus 0 plus Ez, 2 times 10 to the 4, times 0.01 meters squared, gives us 200 newtons per coulomb times meters squared. So there's the net electric flux through the front face of that box. I think I'm going to stress again here. If we look at this value of flux, I don't have a direction. There's no I, J, and K there. It's just a number. Did you have a question?
Yeah, I'm just wondering about like the units. Like it's weird to me that we're multiplying 2 different units. Now I guess it makes sense because the overall unit of flux is all of them.
Yeah, it's electric field with area, right?
Yeah.
It's just like velocity. We divide meters and seconds to get a new meaning of meters per second. We're just more familiar with velocity than we are with flux.
Right.
Yeah.
Okay.
Yeah, no, it's weird though, right? Yeah. Your book is a little bit wishy-washy on flux as a scalar. And your book, if you read through it, I think it has some places where it says the flux has a direction, right? So it will actually give a direction to flux. But flux doesn't have a direction because it's a scalar, no more than temperature has a direction. The sign, however, is meaningful, just like the sign of temperature is meaningful. If temperature is positive, it's warm. If temperature is negative, it's cold. That doesn't mean it has a direction, right? If flux is positive, it means that electric field lines come out through the surface. It means they're in the same direction. If flux is negative, it means electric field lines point into the surface. They're anti-parallel. Your book doesn't really make that distinction. So it says that the flux is inward or outwards, but that is a complete misnomer, and you shouldn't write that down because inward and outward is a direction, and this is a scalar. Okay. Questions about this there? So for a homework question, and this is going to give you lots of practice, we found the flux through this face. Find the flux through the other 5 faces. Okay, you should be able to copy a lot of your work. It all follows the same method. And then this part should really help you get a head start on what Gauss's law means. After you find the total flux, after you add it all up, does that give you any ideas about how much charge is in the box, about what's in the box? So that's something to think about. And let's see what's next. Oh, and actually next I want to do flux around a positive charge. And I don't really want to get interrupted. So let's just quit a couple minutes early and we'll pick up with that on Monday.